Okay, quadratic functions today. And as usual, I like to start with something that you know. So we'll start with linear functions as a comparison. Okay, linear functions look like f of x equals mx plus b. They're characterized by have a constant rate of change, which on a graph looks like slope. Okay, quadratic function. Oh, we say this is a polynomial of degree 1 because the highest powered term has an exponent of 1 on the x, on the variable. Quadratic functions they look like f of x equals ax squared plus bx plus c in their standard form. And you notice here that this is a polynomial of degree 2. And these guys have a graph is a parabola. Okay. The rate of change is not constant, so we call this a variable rate of change, which gives the curve a curved shape. But if I were to make a table of values of x squared, which is the standard quadratic function, 0, 1, 2, 3, 4, 5 for x produces 0, 1, 4, 9, 16, 25 for x squared. And you can see that the rate of change the slope at each interval of size 1, really, so the denominator is just 1, so it's just from 0 to 1 we have 1 over 1. From 1 to 2 we have 3 over 1. From 2 to 3 we have 5 over 1, so forth and so on down to 7 and 9 over 1. But interestingly, if you look at what we call the second rate of change, or the rate of change of the rate of change, okay, and we look at the values 1 to 3, that's going to produce a rate of change of 2 over 1. 3 to 5 is 2 over 1. 5 to 7 is 2 over 1. And 7 to 9 is 2 over 1. We see here that the second rate of change is constant. This is a characteristic of quadratic functions. So degree 1 of linear functions, first rate of change is constant. Degree 2, quadratic functions, second rate of change is constant. That pattern will hold forward for polynomials of degree 3. The third rate of change will be constant, and so on and so forth. So a polynomial function of degree n will have its nth rate of change constant. Okay, I'm assuming that you've had some work with quadratics, and you know that their graphs are parabolas. And parabolas have a vertical axis of symmetry and a vertex. So some parabola, maybe it looks like this. Okay, maybe this is the axis of symmetry, and the vertex is here. And the other key feature is that they often have zeros. It's not required that they have zeros. They can have at most 2. They could have 0 zeros, 1 0, or 2 zeros, but I've drawn one that has 2. And if you notice that the axis of symmetry falls midway between the zeros. And if the function doesn't have any zeros, or if you draw any horizontal line at all, the axis of symmetry will always fall at an x value halfway between the intersection points of any horizontal line and the parabola. So had I drawn, say, not an x-axis, but had I drawn, say, this horizontal line and marked these two intersection points, the axis of symmetry still lies halfway between those two x values. And these are key features of parabolas. So let's take a look at a specific example. What if we have f of x equals x squared minus x minus 6? Okay. If you want to find out the axis of symmetry and the zeros and the vertex, it's often easiest to find the zeros, and then you can use the symmetry to your advantage. So to find the zeros, we set this equal to 0. In this particular quadratic, you can factor into x minus 3, x plus 2 equals 0. So therefore the zeros are x equals 3 and x equals negative 2 are zeros, meaning the axis of symmetry falls at the average of these two. X equals 3 plus negative 2 over 2, which is 1/2. Okay. Now, that's just the x coordinate of the vertex. How do we find the y coordinate of the vertex? Well, we can just find out what f of 1/2 is, because if I know the x coordinate of a point on a curve, I can find the y coordinate by just plugging in that x value and producing a y coordinate. 1/2 squared minus 1/2 minus 6 is equal to 1/4 minus 1/2 minus 6, which is negative 1/4 minus 6, which is negative 6 1/4, otherwise known as negative 25 fourths. Okay, so this particular parabola is going to look like okay, here's negative 2 here, here's 3 here, and we have 0 around here, and that means my axis of symmetry is going to fall around here, which is x equals positive 1/2. And I know this parabola opens upward because the leading coefficient is positive. So I can mark these 2 points as points on the curve. Notice I haven't drawn a y-axis because I don't want to give any indication of the vertical scale yet. I just know that the vertex has to be along this point, along this axis. So I'm just going to mark it arbitrarily there, and then trace a curve that has a vertex there. So it's its lowest point there, and that's going to come back up through here in perfect symmetry. Okay, looks pretty good. Now I don't know what the y coordinate of that, I'm sorry, I just calculated what the y coordinate of that vertex is. It's going to be y equals negative 25 over 4. I also happen to know what if I draw the y-axis now, I also have to know what the y-intercept is. If I put 0 in for x, so f of 0 is going to equal 0 minus 6, which is equal to negative 6. So I know that this point here has a y-coordinate of negative 6. So it's 0 comma negative 6. And the green point is 1/2 comma negative 25 fourths, which is a little less than 6, a little below 6. Okay, that was easy because the function was factorable. I could locate the zeros easily, and then I could find the vertex as an x coordinate halfway between those values. What happens if the function is not factorable? So let's pitch one of those. If we did g of x equals x squared plus 2x plus 9, you can recognize that function is not factorable because factors of 9 don't add up to be 2. And so what do? Well, we do a thing called completing the square, and we That's going to help us locate zeros and a vertex. So what we want to do is add something to this portion and then subtract an equal quantity outside so that we don't alter the value of the polynomial. We just want to add and subtract the same amounts. I want to add something so that what's inside those parentheses is a perfect square trinomial, and that value here happens to be 1. And then we're going to subtract 1 outside so as to not change the value of the whole equation. This perfect square trinomial result, the factorization of that is x plus 1 squared, and I'm left out here with plus 8. Now if I want to find the zeros of this polynomial, or this quadratic, I would set this quantity equal to 0. X plus 1 squared plus 8 equals 0. I get x plus 1 squared equals negative 8, and I go, uh-oh, no number squared equals negative 8. So the conclusion is, therefore, there are no zeros, which is possible. We have a parabola that opens up. It could very well just not get low enough to touch the x-axis. Unfortunately, this puts a roadblock in us being able to find the vertex. We're going to come back to this problem in a minute, because we can actually find the vertex of this parabola, but not by way of the method of first finding the zeros and then locating the midway point between the two. So let's look at another one, and we'll come back to this one, and we'll recognize that there is something you can do. So h of x is equal to x squared minus 2x minus 9. Still not factorable, but maybe it'll have zeros. Let's try the same process of completing the square. X squared minus 2x plus some number here minus 9 minus that same number here. And again, that number happens to be 1. Okay, just by knowing how to complete the square. Here we have x minus 1 squared minus 10. And to find the zeros, I set this equation, I did it again, this equation equal to 0. I get x minus 1 squared equals 10. That's okay. So far, so good. I get x minus 1 is equal to plus or minus 10. X is going to equal 1 plus or minus 10. Sorry, it's plus or minus root 10. So then when I go to say get a picture of this graph, of this parabola, I'm going to start again with the horizontal axis here. I'm going to mark 1, and then I'm going to add root 10 and subtract root 10 from that quantity. Square root of 10 is a little bit bigger than 3, because 3 squared is 9. So I'm going to mark 4, and I'm going to mark negative 2. I'm going to put 2 dots just a little bit past those two values. It's just a rough sketch, that's good. And notice now that what that means is that 1 is the vertical axis of symmetry. I had to add root 10 and subtract root 10 to get to the zeros, therefore 1 must be the middle value. Okay, so now we get a parabola that looks something like this. Comes down to its lowest point somewhere here, and does the same jig, does the same jig over here. Now the vertical axis is somewhere in here, 0. I didn't draw it. I'm usually not interested in it until much later on my sketches. And I know that the y-intercept here is going to be negative 9. That's negative 9. But I'm still looking for the value of that vertex, and I can find out what it is by just doing h of 1. h of 1 is 1 squared minus 2 times 1 minus 9, which is 1 minus 2 minus 9, which is equal to negative 10. So I have here the vertex of 1 comma negative 10. Okay, now what's interesting about this is that if you look back at this form right here, it looks like the coordinates of the vertex are sitting right there, 1 and 10. and it reveals the following, what we call vertex form. So vertex form. If you have a parabola in the shape of y equals x minus h squared plus k, then you're going to have the vertex at hk. Okay, and that way we can go back up to this problem we were looking at before. We can locate that same form, which is right here, and we can conclude the vertex must be -1, 8. Okay, -1 because the form is, remember, x minus h squared plus k. In order to get a +1 in there, h has to be -1. Okay, so we can apply that vertex form here to understand that the vertex is -1, 8, and we don't even need to have any zeros to be able to do that. Okay, but I think it's still important to recognize that the axis of symmetry falls halfway between the zeros. So now we've covered, you can factor it, that's easy. If you can't factor it, you can still try to solve for the zeros. If there aren't any zeros, you just have to rely on vertex form. But let's do one more bit here, which is to let's work with any old generic quadratic. That's going to look like ax squared plus bx plus c. And let's try to figure out vertex form from this guy, which is going to be the derivation of the quadratic formula. Okay, but the quadratic formula, a lot of kids just sort of memorize, is simply a solution of this equation equal to 0 by way of completing the square. The same thing we've done in the last two problems. It just gets more difficult because we have a's, b's, and c's instead of nice numbers, and we have to complete the square with a coefficient on the first term. But bear with me and let's just do it out. The first thing you do is factor out that a, x squared plus b over a x. I don't know what's going to go here. As before, I leave the constant term outside. I'm going to subtract an equal amount there. I'm going to leave this equal to 0. How do we determine what goes here? Well, if you look carefully at perfect square trinomials, let's look at a generic one, something like m plus n squared is equal to m squared plus 2mn plus n squared. Okay, you can see that the value of this middle term is 2mn. Okay, it's twice the product of the two guys sitting here and here. Okay, so we're looking at here at b over a. B over a, actually including x, b over ax is twice the product of x and whatever that third term is going to be. So if we set this up, the next term is going to be, the next line is going to look like x plus something squared. What is that something is the question. Well, it turns out that what goes in the spot of n, which is sort of the unknown thing over here, what goes in this spot, well, you drop the x, like you're going to drop the m, and then you're going to take half of what's left. So half of b over a is b over 2a. And then I have to square that quantity. Okay, we're looking for this guy out here. I take half of 2n, and then I square it. So I have to square this guy. Half of b over a, and then squared. Okay, and then when I figure out what I want to subtract out here, I have to recognize that the a here is going to be distributed to this thing I just put in there. So I have to subtract a times b over 2a squared. That's the hard part. I mean, that's the hardest part of all this proof, is completing the square with these unknown variables, or these parameters, and then recognizing it to multiply by that a. But if you can understand that so far, we're in great shape. What goes in this spot down here is just the quantity of n. If we're looking at n squared here, this is just going to be n, which is b over 2a. Okay, and then we have plus c, and then I'm going to simplify this to be minus, this is b squared, 2a squared is 4a squared, but I'm going to drop one of those a's because it's going to divide with the a in front. So we'll get 4a, and that's equal to 0. Okay, the rest is just playing with the algebra. Okay, we have now our job is to solve for x. Okay, so we say a x plus b over 2a squared, and then I'm going to put a common denominator here of 4a, which makes the numerator 4ac minus b squared. And you can smell the quadratic formula in there. Okay. What we're looking at actually right here is form. I mean, what this says is the vertex of a quadratic is negative b over 2a, comma, 4ac minus b squared over 4a. That's a mouthful, but it's not worth memorizing, but there it is. It might be worth memorizing, though, that the axis of symmetry is sitting right here. The vertex of a quadratic is always on the vertical line negative b over 2a. Worth thinking about while we pause here. Going on to solve for x, I'll just subtract a x plus b over 2a squared. I'm going to subtract this big quantity. I'm going to get the opposite of 4ac minus b squared over 4a. And the first thing I'm going to do when I see the opposite of a subtracted quantity like that, I'm going to commute the subtraction to make it b squared minus 4ac over 4a. Leave this side alone. Okay. And now we have to divide both sides by a. B squared minus 4ac. To divide by a is to multiply the denominator by a, so I'll add another a down here. Now I'm ready to take the square root. Plus or minus the square root of b squared minus 4ac over 4a squared. And that's simplifiable to plus or minus just the numerator, b squared minus 4ac over 2a. Okay, good. And now I have x equals, and I'm going to subtract b over 2a from both sides, but instead of subtracting at the end, I'm going to put it at the beginning. I'm going to make it negative b over 2a plus or minus square root of b squared minus 4ac over 2a. Okay, now before I combine those fractions, it's worth looking again. You can see this is the axis of symmetry. Because I'm adding and subtracting the same quantity, so to draw a graph, it would look something like, I mark negative b over 2a. I'm going to add plus the square root of b squared minus 4ac over 2a on one side. I'm going to subtract negative b over 2a plus negative b over 2a minus the square root of b squared minus 4ac over 2a. Okay, I can mark these 2 points on the graph just like I did prior. I know there's a lot of letters and it's sort of a mouthful, but the concept is identical. And here's my axis of symmetry coming right down through negative b over 2a. Okay. Again, these are some details I think you miss if you memorize the thing I'm about to write, which is just x equals negative b plus or minus the square root b squared minus 4ac over 2a. That's the quadratic formula. What it produces is these are the zeros of a quadratic of the form y equals ax squared plus bx plus c. Okay, so that's the proof of the quadratic formula. Okay, the last bit I want to do here is just to recognize, just to follow up what we've done. The key takeaways here for quadratic functions are the second rate of change is constant. We've got the zeros of any quadratic are x equal negative b plus or minus the square root b squared minus 4ac over 2a. And we have the axis of symmetry is x equals negative b over 2a. I should say this is okay. And then finally, we touched upon the idea of vertex form. Y equals a times x minus h squared plus k, which can be obtained by completing the square, or you can just find the zeros and then find the vertex and put it in this form if you don't like to complete the square, which I don't. I think you can complete the square one time in the proof of the quadratic formula, and then that's it. You don't need it from then on out. Finally, we have standard form y equals ax squared plus bx plus c. Okay. As an addendum, as sort of an optional sort of bonus analysis, let's look at the quadratic formula. The result of y equals ax squared plus bx plus c equals 0 is x equals negative b plus or minus the square root b squared minus 4ac over 2a. Okay. We can analyze to determine if the function will have zeros by looking at this piece underneath the radical, which is called the discriminant. Okay, it helps you discriminate whether there are zeros for the quadratic. Notice that the discriminant is underneath a radical. If you have a number that's underneath the radical that's negative, then you have an imaginary number which won't show up on a real number axis system, meaning it won't show up at all on a graph. If you have the value of 0, then you'll only have one number come out. That'll be negative b over 2a. And if you have a positive number, then you'll get two numbers out, negative b plus that positive number, the square root of that positive number, and negative b minus the square root of that positive number over 2a. So that's just the introduction to the analysis. Let's just go case by case here. If, let me just summarize that, if the discriminant b squared minus 4ac is negative, then the parabola has no real zeros, meaning it won't show up on a normal graph. If b squared minus 4ac equals 0, then x equals negative b over 2a is the only 0. And notice that it falls on the axis of symmetry, which means that the 0 will be the vertex. Okay, some people call this a double 0 because one point is playing the role of 2. And if b squared minus 4ac is positive, then the parabola will have two zeros. And finally, one little sub case here is if that number is positive and if b squared minus 4ac equals a perfect square, okay, notice that it's something underneath a square root, so if it's a perfect square, then it's going to sort of tumble nicely down into some other number. Then the two zeros are nice rational numbers. Now, I don't really like using the word nice, but I'll put it in quotation marks. They're all nice, but people like rational numbers a little better. Okay. Also, this means that the quadratic could have been easily factored. Maybe not easily. I'll put easily in quotation marks. Okay, I mean, that's really a nice 30-minute summary of what sort of all you need to know about quadratics. I think that that should be clear with some review. Maybe you've covered this in other classes, but maybe not all in one 30-minute little chunk. So I hope that's clear.